In this video, we'll discuss computing functions or limits of functions of several variables. In particular, we're going to talk about limits of continuous functions. If the function's continuous, we're just going to plug in the xy or the xyz that was given to us, and that's going to give us the right answer. We're going to talk about what it means for a function of several variables to be continuous at a point. And we will also eliminate 0 over 0 indeterminate forms using the three techniques that we discussed at the beginning of Calculus 1. So if you remember these limits from the beginning of Calculus 1, there's really nothing new here. Just instead of having functions of x that give you 0 over 0 indeterminate forms, you're going to have functions of x and y, or potentially functions of x, y, and z. So let's look at this first example. We'll learn by example. I've got the limit as xy approaches 1 over 27 and pi cubed of this function. Now, a cosine function is continuous as long as it's well defined, and this cube root of xy is going to be well defined no matter what x is and no matter what y is. I can take the cube root of any product, positive, negative, 0, it does not matter what that number is, I can take its cube root, and then the cosine of any number is well defined as well. So this function is continuous. I can plug in any xy that I want, and I'm going to get the right value out. So the solution to this, the value of this limit is just the cosine of the cube root of x times y, and I'm going to substitute in my x, which is 1 over 27. I'm going to substitute in my y, which is pi cubed, and we're just going to simplify. Well, the cube root of 1 over 27 is 1 over 3, because the cube root of 27 is 3, and the cube root of pi cubed is pi. So we end up with cosine of pi over 3. So that's cosine of 60 degrees. If you don't remember, it's probably been a little while. We've got a 60, 30, 90 triangle right here. Opposite the 60 is a square root of 3. Opposite the hypotenuse is a 2. Opposite the 30 is a 1. That's from trig, and all of that is derived in trigonometry. So according to this, the cosine of 60 is adjacent over hypotenuse. Remember, SOHCAHTOA, adjacent over hypotenuse, is going to be 1/2. And 60 degrees is the same as pi over 3 radians, because pi is 180. 180 divided by 3 is 60. So the cosine of pi over 3 is 1/2. That's the value of the limit. So it's that easy. If the function's continuous, just plug in the point. That's going to give you the right answer. Now let's look at this. Is this function continuous at x equals 3 and y equals -6? Well, sure. I can't divide by 0, but x isn't 0. And I can't divide by 0 here. Y isn't 0. So we just plug in the x and the y. We've got 1 over x minus 4 over y, and we're going to square the result. X is 3. Y is -6. So we've got 1/3 minus a minus is a plus. That reduces to 2/3. 1/3 plus 2/3 is 1. 1 squared is 1. So our limiting value is 1 there. So you see, it's really easy. If the function's continuous, you just plug in the point. And we know it's continuous if you're just given a formula, and that formula is well defined. We're going to look at some functions and decide exactly where they're continuous in a little bit. Now, if the function is not well defined at the point, then you might have to do some of these things that we did back in Calculus 1. You might have to factor and reduce. We might have to multiply or divide by the Pythagorean conjugate. Multiply and divide by the Pythagorean conjugate, or clear complex fractions. So let's look at this one and see if this is well defined. At xy equals 2, -4, well, I've got this function. Notice that if y is -4, the numerator is 0. So I'm just going to do the math. I'm going to work out the numerator. So I've got -4 plus 4 is 0. And the denominator, that's x squared times y minus x times y plus 4 times x squared minus 4 times x. I'm replacing all the x's with 2's. So that's 2 squared minus 2, 2 squared, and 2. and I'm replacing all of the y's with -4. So that's a -4, and that's a -4. Okay, let's see what we get. Well, that's 4 times -4 is -16. A -2 times a -4 is +8. 4 times 4 is +16, and we got a -8 there. -16 plus 16 is 0. 8 minus 8 is 0, so we get 0. So this is a 0 over 0 indeterminate form. Now remember what we did in Calculus 1. If you have a polynomial divided by a polynomial, and we do, these are just powers of x and y, all the powers are positive, they're multiplied together, and then they're added to each other. Anytime you've got a polynomial or a polynomial, it's a rational function. We use the same technique. If we got 0 over 0, we factored the numerator and denominator as much as possible, and we were hoping that we'd see the same factor in the numerator and denominator so that they would cancel and so that we could take the limit and be done with it. So let's see if that happens here. Hopefully it does. Most of the time it does. So I'm saying that limit is equal to this. And what I'm looking to do now is I'm looking to factor and reduce. Now that numerator doesn't simplify at all. But in the denominator, I might be able to simplify things a little bit. Notice that both of these terms have a y in common, and both of these terms have a 4 in common. These also have a 4 and an x in common. So with that in mind, I'm going to group the first two together, and I'm going to group the last two together, and I'm going to factor out any common factors that I see. This is called factoring by grouping, but you've got polynomials in x and y, so it feels a little different than it probably did in pre-algebra class. So I'm looking at x squared y and minus xy, and I want to factor out anything that they both have in common. Well, they both have an x, so I'm going to factor that out, and they both have a y, so I'm going to factor that out. And I just ask myself, pre-calculus style, xy times what gives me x squared y? Well, just one x is missing. And xy times what gives me a negative xy? Well, it's just a -1. Okay. Over here, same thing. What do they have in common? They have a 4 in common, so I'm going to factor that out. They also have an x in common. I've got an x squared and an x. Factor that out. So I ask myself, 4x times what gives me 4x squared? Well, that's an x. 4x times what gives me the -4x? That's a -1. So now I look at this group and this group. What do these two groups have in common? I hope you said x minus 1, because that's what they have in common. They do. So we can factor that further. And there are all these restrictions. I'm not going to keep writing them down, but I'll refer back to them later. Got a y plus 4 in the numerator. And down here, I have an x minus 1 in common. So I'm going to take that out. And I ask myself again, x minus 1 times what gives me the first group? Well, I took out the x minus 1. What was left is the xy. And then I say to myself, x minus 1 times what gives me the second group? Well, the only thing that's missing is the 4x. Now, at this point, I might be disappointed because I don't see anything canceling. So I ask myself, okay, is there anything I could factor further? I don't know how I missed it earlier, but all these guys had an x in common. I could have factored that out from everything first. I missed that, but I didn't miss it down here. Look at the xy and the 4x. I could factor out an x from that. So I'm going to factor out an x from that. I've got y plus 4 in the numerator, x minus 1 in the denominator. This is x times the quantity y plus 4. X times y gives me xy. X times 4 gives me 4x. And look, the y plus 4's reduce. And now you've got 1 over x times x minus 1. Question is this function continuous there? Can I plug in x equals 2 and get a number out that makes sense? I sure can. I'm not dividing by 0 anymore. So this is called factoring and reducing. We factor as much as possible, we reduce where we can. And once we've reduced that factor that gave us the 0 over 0, we're left with something that's continuous at this point. So we just replace x with 2, and we replace, we would replace y with negative 4, but there are no y's left, and we get 1/2. All right, so that's that. Okay, and actually I think this is that restriction's not supposed to be x is not equal to 4. It's supposed to be the restriction y is not equal to negative 4. So we don't have that 0 over 0. We're not on that line where y equals negative 4. Okay, so we have factored and reduced. That's one way to get rid of 0 over 0 indeterminate forms. Let's look at another example. Also Calc 1 style. Look at that. Now if that was a 1 and that was a 1, or not a 1, but I mean, if I plugged in x equals 2 here, let's say the y's were gone. So I had the square root of 2x minus 2 over 2x minus 4. Let's say that there were no y's. Well, at x equals 2, I get square root of 4 minus 2. So square root of 4 is 2. 2 minus 2 is 0. And then when x equals 2, 2x is 4. 2 times 2 is 4 minus 4 is 0. So this would be an indeterminate form if it was just the limit as x approaches 2. Now it's got a y in it, but as y approaches 2, 0, let's look at what happens to the numerator. The numerator is going to be the square root of 2 times my x value, which is 2, minus 0, minus 2. Square root of 4 is 2, 2 minus 2 is 0. And the denominator is 2 times x minus y minus 4. X is 2, y is 0, so we got 4 minus 4, which is 0. So this is a 0 over 0 indeterminate form. All right, I know how to handle this. Back in Calculus 1, we said this is no big deal. We're just going to multiply and divide by the conjugate. Now, remember what the conjugate is. The conjugate of a plus b is a minus b, and vice versa. We multiply by the conjugate every time we saw these roots back in Calculus 1. Now, when you are looking at the conjugate of this numerator, that's exactly what we're going to have to multiply by. This is your a. That whole square root is your a, and that 2 is your b. So the conjugate of this is this exact same square root with the minus there and everything, and you change that minus to a plus. So we're going to have the limit as xy approaches 2, 0 of this and we're going to multiply and divide by the Pythagorean conjugate. So we're going to multiply by the conjugate of this. That stays the same, the 2 stays the same, but that minus becomes a plus. And you're going to do the same thing in the denominator. Okay. Now, be careful here. You don't want to distribute in the denominator. It's just going to make things worse. But you do want to distribute in the numerator. First times first, it's a square root times itself. That's just going to give you whatever's under the radical. Provided that what's under the radical is positive, but we're just going to assume that it's positive. So we get 2x minus y. Outer times outer is 2 of those roots. Inner times inner is minus 2 of those roots. So those cancel. That's always going to happen when you multiply conjugates together, because we get first times first is a squared. Outer times outer is minus ab. Inner times inner is plus ab. Last times last is negative b squared. So those are always going to reduce. We're going to have a squared minus b squared every time. But if you're not sure, FOIL, this times this is 2 times, or positive 2 times its square root. This times this is a negative 2 times its square root, so they're gone. And last times last is a negative 2 times a positive 2, which is going to give me a negative 4. You see it? There's a common factor. that works out. So that reduces with that, and you get that. Now the question becomes, okay, when I plug in 2, 0 now, do I have a 0 over 0 indeterminate form anymore? Well, no. Multiplying by the conjugate got rid of it. So this multiplying by the conjugate works, because usually after you distribute, you end up factoring and reducing, and you get something that is continuous. This function is continuous at this point. So now we can just plug in x equals 2, y equals 0. Square root of 4 is 2, so I just get 1/4. All right. So that's multiplying by the conjugate. When you see a radical like this, and you have a 0 over 0 indeterminate form, so you plug in 2, 0, you get 0 divided by 0. Then try multiplying by the conjugate. Often when you do, when you distribute those conjugates, so you get the a squared minus b squared when you're done. Often when you do, that is going to become a factor that reduces with something down here. It doesn't always happen immediately. Sometimes you have to factor a little bit further. Sometimes you might have to do a little bit more algebra. But after doing some algebra, you're going to see a common factor in the numerator and the denominator. Most of the time, you're going to cancel it, and then you're going to have a continuous function that's left. So you just plug in the 2 and the 0, and you're done. Okay. Now, this last one has got fractions. Fractions within a fraction. We call this a complex fraction. Now, if this is continuous at 4, 3, I want to just plug in 4, 3 and be done. But if it's not continuous, then there might be more work to do. We might have to do a little bit of algebra and then calculate the limit. So let's look at just the numerator first. The numerator is 1 over the square root of y plus 1. Y is 3. Then I'm subtracting 1 over square root of x. X is 4. So I've got 1 over square root of 4 minus 1 over square root of 4, which is 0. And the denominator is x cubed. X is 4, so that's 4 cubed minus x squared. So 4 squared times y, which is 3, minus x squared, 4 squared. So I get, 64. And then 16 times 3, what's that? 48. Minus another 16. What's negative 48 minus 16? I think that's 64, guys. It's 64 minus 64, which is 0. So this is a 0 over 0 indeterminate form. Okay. And I see fractions within a fraction. So what we always do, whenever we have fractions within a fraction and we've got a 0 over 0 indeterminate form, is we multiply by the least common denominator of the smaller fractions in our problem. So this is just a single enormous denominator. There are no fractions down here. But these smaller fractions, they don't have any factors in common. They're denominators. Since their denominators don't have any factors in common, the LCD is just this times this. So we're going to multiply the whole fraction by the LCD of these guys. Least common denominator. It's going to be the square root of x times the square root of y plus 1. And we're going to multiply the numerator of this fraction by the LCD and the denominator of this fraction by the LCD. Now you could just get a common denominator and then divide. That will work as well. I like this better because it's cleaner and nicer. It simplifies really quickly. But if it's not intuitive to you, you go ahead and get a common denominator instead. That'd be just fine. It's equivalent. Your way's just got a little bit more work if you decide to get a common denominator first. Okay. So we're multiplying everything up here by square root of x times square root of y plus 1. That's legal as long as we also multiply everything down here by the square root of x times the square root of y plus 1. Now you've got multiple terms up here, so you're going to distribute. Down here I'm going to leave it factored. My hope is that leaving it factored will make it easier to cancel common factors later. So I distribute this times that, actually I think I'm just going to write it out. We've got square root of x times y plus 1 times the first term, minus 1 over square root of x times square root of x times square root of y plus 1, all divided by all of this down here. Now, I notice I've got a bunch of x squareds in common here, so I'm going to factor that out as well. X squared times x gives me x cubed. X squared times a negative y gives me that term. And x squared times a negative 1 would give me that negative x squared. I still have the square root of x and the square root of y plus 1 here. Okay, now the whole point of multiplying by that LCD was to clear the fractions. Notice when I distribute the LCD, the y plus 1's reduce and the square roots of x reduce. So now I'm here. I've got the square root of x minus the square root of y plus 1, all divided by x squared times x minus y minus 1 times the square root of x times the square root of y plus 1. Okay, are we done yet? If I plug in 4, 3, square root of 4 is 2, square root of 3 plus 1 is square root of 4. It's another 2, 2 minus 2 is 0. I plug in 4, 3 down here. 4 minus 3 is 1, 1 minus 1 is 0. So we have another 0 over 0 indeterminate form. But we don't have any fractions within our fraction anymore, which is a very good thing. But I notice I've got some radicals, so I'm going to multiply by the conjugate. We're going to go back to this method. As soon as I see something like this, just a single fraction, it's got a radical in it, I've got a 0 over 0 indeterminate form, I'm going to try this technique, try this approach. This is a 0 over 0 indeterminate form. I'm going to multiply by the conjugate of that guy. And that's legal as long as I also divide by the same thing. Now in the numerator you want to distribute first times first, outer times outer, inner times inner, and last times last. In the denominator, you want everything factored as much as possible because we're hoping something will cancel with what we get in the numerator. So I've got x squared and x minus y minus 1, square root of x, square root of y plus 1, and the square root of x plus the square root of y plus 1 as another quantity. Now first times first up here gives me an x. Outer times outer is a positive square root times a positive square root. Inner times inner is the same thing but negative, so those are going to reduce. Last times last is a minus this quantity. Square root of y plus 1 times square root of y plus 1 is y plus 1. Be careful, you need parentheses there. If you distribute that negative, hey, you get an x minus y minus 1 and an x minus y minus 1 right there. That's nice. So I'm going to do that on the next page. Oops. All kinds of other problems from other classes. Trying to recycle these papers. Not recycle, I guess I'm just reusing them before I recycle them. Go through so much paper, we want to save a tree where we can. Okay, so we've got xy, it's approaching 4, 3. And in our numerator we've got x minus y minus 1, all divided by x squared times x minus y minus 1 times the square root of x times the square root of y plus 1 times this quantity. Oops, that's kind of sideways. There we go. And we can reduce those common factors. Now I've got a 1 in the numerator. It's definitely not a 0 over 0 indeterminate form anymore. Hopefully this isn't 0. If it is 0, maybe our function's going to infinity. But it doesn't look like it is. It looks like we're adding and multiplying a bunch of terms. So I think it's going to work out just fine. This is continuous at 4, 3. So you're just going to replace x with 4. So we've got 4 squared there. Times the square root of 4 times the square root of y plus 1. Y is 3. And then on that last piece, we've got the square root of x and the square root of y plus 1 over here. Okay. Now let's simplify. This is 1 over. We've got 16. Square root of 4 is 2. Square root of 4 is another 2. And that is 2 plus 2, so that's another 4. So it looks like I've got 16 times 4 times 4, so 16 squared. What's 16 squared, guys? 96. Yeah, that's what I thought. 256. So 1 over 256. That's our limit. Now if you're saying to yourself, what on earth does all of this mean? Remember what we talked about in the last video. As xy gets arbitrarily close to this point, the z-values on our graph, for this graph, get arbitrarily close to 1/2. Turns out that that's exactly what the z-values are, the z-value is at that point, because this function's continuous there. This one's also continuous. If I plug in this value, I get the value of the function there, I get 1. Now this one is undefined at this point. We get a 0 over 0 indeterminate form, but we could factor and reduce. That was our first method for getting rid of the 0 over 0. And eventually, we get a 1/2. Or, look at something like this. That turned out to be a 0 over 0 indeterminate form. It had a radical in it. So I multiplied and divided by the conjugate. Distribute the conjugates, leave everything else factored. Factor more if you need to. Reduce common factors, and then evaluate the limit that results. So this is telling us that as xy approaches 2, 0, the z-values on our graph get very close to 1/4. Now they don't actually get to 1/4. This function might have a hole in it. It might have an issue along the line x or 2x minus y equals 4. Because if 2x minus y equals 4, that's going to be 0 all the time. As long as we're not on that line, the z-values are getting very close to 1/4. Now here, at 4, 3, the values on this graph, or this function is undefined because we get a 0 over 0 indeterminate form. Now, if we clear the complex fractions by multiplying by the LCD in the numerator and denominator, that gets us a little bit closer. Now this time, clearing complex fractions, was not enough. We still had conjugates when we were done, so we had to multiply and divide by the conjugate again. And then, once we multiplied by the conjugate and distributed, we saw we had a common factor, so we had to reduce common factors. Finally, we were at a point where the function that was left after simplification was continuous. So we just plugged in x equals 4 and y equals 3, and we got this number. So this function, the original function, before all that simplification, as x approaches 4, 3, as xy approaches 4, 3, as we get closer and closer and closer to this point in the xy plane, the z-values get close to this value. But they never actually get there. They get arbitrarily close. I guess our surface is probably going to have a hole in it there. Or maybe our surface is not well defined for the entire line, x minus y equals 1, because that's when we'd have a 0 over 0 there. Okay, guys, so that is eliminating our 0 over 0 indeterminate forms. Now, we've talked about limits of continuous functions. We said if you can plug in the value and you get the right thing out, then the function is continuous there. I want to give you the formal definition of continuity. Now that means, intuitively, we say a function of several variables is continuous if it's one piece. So we have the surface given by z equals f of xy is one continuous piece. And I know I'm using continuous in my intuitive definition of continuous. I'm sorry. Doesn't necessarily even have to be smooth. It could have some sharp corners in it. Maybe you've got a fold in it, like a page with a fold in it. That's okay. It's still continuous. If the whole surface could be made with one piece of paper, that's going to work just fine. Now, if you've got w equals f of x, y, and z, it's not going to be as easy to see intuitively, but that's the idea. Now, you say, okay, well, if I can't see it, then how do I define it? Well, if I want to define continuity formally, remember what we did in Calculus 1. We said a function is continuous at a certain x value if this limit exists and the function value exists and the limit and the function value are the same thing. So those were the three characteristics we were looking for. So the limit exists at x equals a, f of a exists, it's well defined, and the limit as x approaches a of f of x is equal to that limit, or is equal to f of a. That's Calc 1 style. Calc 3 style, we're saying xy is going to approach x naught, y naught for some function of two variables f of x, y. If the limit exists and the function value exists and they're the same, the function is continuous there. Or just think about actually evaluating this function, or evaluating this limit. You have this. If you can plug in x naught, y naught, and you get a value out that makes sense, it's continuous there. So you're good to go. That's a function of two variables. Now, the same thing works for a function of three variables. We could be approaching x naught, y naught, z naught. Well, if the limit exists and the function value exists and they're the same thing, this function is continuous at that point. So this one is continuous at x equals a. This one is continuous at xy equals x naught, y naught. This one is continuous at xyz equals x naught, y naught, z naught. Now, if these limits and function values are the same for all x, y, z in a certain region in 2 dimensions, or in a certain spatial region in 3 dimensions, then we say that the function is continuous over that region. The n-dimensional analog of this is, let's say you've got x1 through xn, and it's approaching a sub 1 through a sub n. And we want to find out what happens to this function. If all you have to do to find the limit is plug in a1 through an, if the function value exists and the limit exists and they're the same thing, this function is continuous at the point a1 through an, that ordered n-tuple. Okay, now, with that in mind, let's talk about continuous functions. Pretty much any function that you've discussed in pre-calculus and before that is continuous on its domain. So, root functions, square root, cube root, 4th root, 5th root, 7th root, 8th root, 100th root, it doesn't matter, those are continuous. Polynomial functions, continuous. So those are positive powers of x and y and z and any other variable we want added together and multiplied by constants. Those are polynomials. Rational functions, that's a polynomial divided by a polynomial. Those are continuous as long as the denominator is not 0. The denominator is not 0 on its domain. Trig functions, exponential functions, logs, inverse trig functions, gosh, is there anything else? Did we cover them all? Power functions are special cases of that. Lines are special cases of polynomials. Absolute value is continuous. It's got that V shape. Yeah, all of these functions are continuous on their domains. So if somebody asks you if a function is continuous or where a function is continuous, they're really asking you, what is the function's domain? Because all the functions that we have discussed so far, unless they're a piecewise function, they're defined as in several pieces. On this region, it's this function. In this other region, it's this function, and so on. Unless it's given to you that way, if it's given to you by a formula, those are going to be continuous on their domain. So when somebody asks you where is this function continuous, and they give you a formula, what they're really asking you is, what's the domain of this function? Because the function is going to be continuous on its domain. Okay, so let's look at some functions and think about where they're continuous. Now this one, I notice it's a rational function. I've got a polynomial divided by a polynomial. So it's going to be continuous on its domain. And the only issue here might be dividing by 0. Remember, you can't divide by 0. You can't take even roots of negative numbers. You can't take logs of negative numbers or 0. So let's just factor this, find out when it's 0. And those are going to be the lines or the curves where this function is undefined. Now, the domain of a function of two variables is a subset of two-dimensional space. So if I want to find out where this function is continuous, it's going to be some xy pairs in the xy plane. It's going to be some set of xy pairs in the xy plane where this is well defined. So keep that in mind. With a function of two variables, its domain is a function of two-dimensional space. That means it's going to be continuous on a region in two-dimensional space, or we don't usually call it space, we call it the plane. So let's factor this. That's a difference of squares. Remember from algebra, a squared minus b squared is just a plus b times a minus b. That's all I'm doing here. My a is x. My b, my b squared is 4y squared. So b is the square root of that, so that's a 2y. So I'm going to add 2y and subtract 2y. Now down here, first times first is x squared, so I'm going to have an x there and an x here. Now, last times last has to be a 2y squared. So I think I'm going to have a 2y and a y, so that last times last is 2y squared. Now, I need outer times outer plus inner times inner to give me that negative 3xy, and I think if both of these are negative, that's going to work. Outer times outer is negative xy, inner times inner is negative 2xy, so it's going to be negative 3xy. So this is the factored version of f of xy. And then here's our simplified version. F of xy turns out to be equal to x plus 2y over x minus y. Now, it's tempting. You might want to say that the domain of this function is all of the xy plane except for where this denominator is 0, except for where x minus y is 0. But remember, x minus 2y can't be 0 either, because if x minus 2y is 0, we've got 0 over 0 here. So our domain is going to be a subset of the xy plane. So it's all xy in the xy plane such that x minus y is not 0 and x minus 2y is not 0. And if you rearrange those inequalities, you're saying, well, I want this set of all xy such that, let's solve for y is not equal to x. And let's solve this one for y. X is not equal to 2y, or y is not equal to 1/2 x. Y equals x looks like this. We go up 1 and over 1. Y equals 1/2 x. Starts at the origin, we go up 1. So it's rise over run, up 1 and over 2. the domain is everything else. You might say, I thought they were asking about continuity, and they were. Where is this function continuous? This function is continuous on its domain. So I'll say f is continuous on this region. I'm going to say continuous on D. D is the domain, and this is its domain. It's a set of all x, y, such that x is not equal to y, and y is not equal to 1/2 x. Okay. This one, similar. It's a domain issue. Where is this function continuous? Well, it's got a log in it. You can't take the log of a negative number or 0. So the domain of G is going to be the set of all x, y in R2 such that 2x plus y squared, that's the expression inside the logarithm, it has to be positive. So I'm going to take that and solve for x. So if 2x is greater than negative y squared, or if I divide both sides by 2, I get x is greater than negative 1/2 y squared. You might say, what does that look like? Well, remember that's a parabola on its side. If x was equal to negative 1/2 y squared equal to that, we'd have a parabola that faces down like this. I want to say faces down, but it faces to the left, faces up on the x-axis or down on the x-axis when x is equal to y squared. So it's down on the x-axis is to the left. And x has to be greater than that. And you can choose a test value. Maybe just choose something on the x-axis. Say x equals 3, y equals 0. 3 is definitely greater than 0. So we're going to shade on this side. That's the domain of G. Where is G continuous? G is continuous on its domain. And the domain of G is the set of all x, y in R2 such that x is greater than negative 1/2 y squared. Okay, last one. Notice I've got a function of 3 variables this time. With a function of 3 variables, our domain is a subset of 3-dimensional space. So it's going to be some region. Now I've got a root in this one. So it's the domain is the set of all x, y, z in R3, such that this expression under the square root is positive, or possibly 0. It's okay if it's 0. So I need x squared plus 4y squared plus 9 times the quantity z minus 1 squared minus 36. I need that to be greater than or equal to 0. Now that's an inequality that I can solve, that I can rearrange until it looks like one of the formulas for our surfaces from the first chapter. So we've got x squared plus 4y squared plus 9 times z minus 1 squared minus 36 is greater than or equal to 0. I'm going to add that 36 to both sides. So it gets rid of that and moves it onto that right side. And then I'm going to divide everything by 36 because I see an x squared, a y squared, and a z squared. And if all 3 are positive, all 3 are squared, I need that to be 1, so it's going to look like one of the surfaces that we've studied previously. All right, and so this simplifies. We get x squared over 36, which is 6 squared. 4 goes into 36 9 times, so we've got y squared over 3 squared. 9 goes into 36 4 times, so you've got z minus 1 squared over 2 squared. That's greater than or equal to 1. Ooh, that's interesting. The domain of this is a set of points, and the boundary of that domain is when this equals 1. So that's going to equal 1. Well, that's going to be an ellipsoid. And that equals when we get an ellipsoid centered at x naught, y naught, z naught. And those come from what you're subtracting from the x, the y, and the z. Whatever sign you see there, take the opposite sign. So it's going to be centered at 0, 0. That's a -1, so we're going to see +1. And we go plus and minus 6 units in the x direction from that point. So this is not to scale. And then we're going to go plus and minus 3 units in the y direction from that point. Okay. So that's an ellipse that we're seeing on the plane where z equals 1. And then from that point, we're going to go up 2 to z equals 3 and down 2 to z equals -1. I know it's really ugly, guys. I'm sorry. Imagine with me. Ugh. It's really ugly looking ellipsoid, but that's the idea. Its center is right here at 0, 0, 1. Now, that is the boundary. We are talking about the domain of this, I wrote f, domain of the function h, is a set of all x, y, and z such that this is true. Now, if that was less than or equal to 1, that would be the inside of that ellipsoid. So the domain is the region outside and on the boundary of. Ran out of space, the ellipsoid in the picture. Okay. So let's briefly review. What are we talking about again? Oh yeah. Continuity and limits. So when we're computing limits of functions of several variables, we said if the function's continuous, meaning it's one of those functions that you've studied in a previous class, you can plug in this point, you get out an answer that makes sense. Just go ahead and plug in the point. That's the value of your limit. It's just, all I'm saying is, if the function's continuous, if you can plug in this value and you get the same, and the limit of this function is the same as the function value. So just go ahead and do that if you can. We talked about continuity of functions of several variables in that last part. All the functions that we've studied are continuous on their implied domains, unless it's a piecewise function, and you're not going to study any piecewise functions in this class, not in this section. You're just really looking for the domain if somebody asks you where these functions are continuous. You don't want to divide by 0, you don't want to take even roots of negative numbers, and you don't want to take the log of a negative number or 0. Everywhere else they're continuous. One other thing to worry about is, remember, if the function is a function of 2 variables, the domain is a subset of 2-dimensional space. If it's a function of 3 variables, it's a function of 3-dimensional space. If it's a function of 5 variables, it's the domain is a subset of 5-dimensional space, even though we wouldn't be able to see it. So make sure you keep that in mind, that dimensionality of the domain when you're determining where a function is continuous. Don't say all real numbers if you're talking about the entire xy plane, or if you're talking about all of 3-dimensional space, because all real numbers is just one of those 3 dimensions or 2 dimensions. Now, if you have a 0 over 0 indeterminate form, most of the time those are going to be eliminated using one of these techniques. Now, the problems are a little bit contrived. They're designed so that one of these techniques will work. If you have a 0 over 0 indeterminate form and one of these techniques does not work, that doesn't mean the limit doesn't exist. It just means that the limit can't be evaluated using the techniques from this class or Calculus 1. Now, if you've been thinking, I want the L'Hopital's rule. Why can't I use L'Hopital's rule? Every time I saw a 0 over 0 in Calc 1, I just used L'Hopital's rule. Once I learned that, it was a great trick. Unfortunately, there is no n-dimensional analog for L'Hopital's rule. We can't do it in n dimensions. It just doesn't make sense. So yeah, you're kind of out of luck on that one. It's going to be one of these three techniques, or you'd have to go back to the limit definition of the formal definition of the limit, excuse me. And that tends to be hard. I'm going to save most of those problems for your advanced calculus class if you really like epsilons and deltas and want to prove those things and want to truly understand the details of why a limit exists. You can study it in those classes. So these are the ways that we will show, or that we will find a limit. We'll just plug in a value when the function's continuous there, or we'll get rid of 0 over 0 indeterminate forms like this. And then remember all the functions that are defined by formulas that we've studied in this class, or in this class and previous classes, they're all going to be continuous on their domains. So don't divide by 0, don't take even roots of negative numbers, and don't take the logarithm of a negative number or 0.